Right. A force F needed to break a copper wire of radius R. The force S needed to break a copper wire of radius 2R. So what is common here? Copper is common for both there are two experiments conducted. Hello?
Yes, sir.
So with the given data, what is the presumption you can do? Copper is common. Okay. And they have told a force needed to break a copper wire. The force needed to break a copper wire of radius. So here, simply you have to say, well, I have taken now two copper wires, right? And if you have taken two copper wires, then some things should be presumed to be common here. What are the things that are common here? Well, the length can, do like this. What is it? The Young's modulus is common, isn't it? Young's modulus of copper is straight. How do you represent Young's modulus? By sigma or some other symbol are you using?
Capital Y.
Okay, we are using capital Y, right. So capital Y will be equal to FL by A into delta L, correct?
Yes.
So here in both the experiments, the F is something that you have to see. So in the first experiment, you have taken the force F1, okay, and then you have to take the length also as L and the cross section also A, and the corresponding change will be delta Ly. Clear? Hello?
Yes, sir.
No, sorry. Force F1, this one, and this area is also A1. Okay? Hello? That means now, here you see, the force needed to break. Now, break means what? You understand the concept of breaking. Breaking means what? There is something called as maximum stress that it can take, or the breaking stress. Understood? So, this formula will not be of use. Okay, so what will be useful here? What is the breaking stress? What is the breaking stress? So here you see Y is equal to stress upon strain. Okay. Now if you say it is breaking, then the stress should be the breaking stress. That's what is important. Okay. Young's modulus is same. Only thing is breaking stress. So what is stress here? In the first case it is F1 upon A1. Right? In the second case, it is F2 upon E2. Right? Hello?
Yes, yes, sir.
So, therefore, now you see, strain is not of consequence. Assume that the strain, that is delta L by L, is same for both. So, you will have to simply take it like this. What is it? So, that means now the Young's modulus for both is same, or the Young's modulus now, that is if you still use this formula, right, the strain being same here, it is a matter of F1 by A1, F2 by A2. So in the first case the radius is R1, so this becomes pi R1 square. Second case it becomes pi 2R square. So it becomes 4 pi R square. Correct? Hello?
Yes, sir.
So therefore the force needed to break a copper wire of radius 2R should be 4F. Understood? So if you take this as F, this is this divided by this, so this should be 4F. That is, you need a force of 4 times to break the copper wire of radius 2R. Got it? Because you see, force is after all, it is distributed. Now understand the science behind this. So if this is a cross section, right? In the cross section, if you are applying force here, this force is getting distributed everywhere here. Okay? And this force is getting distributed everywhere here, and then each of these, each of these points are getting pulled by these forces. So now, if you increase the area, then this force gets distributed. That means there is lesser force available at each point to pull it. Okay, so you have to increase the force if you have to break it. That is common sense. Also, will tell you it should become 4F. Okay. Hello. Right. So F1 upon A1 is equal to F2 upon A2. That's it. So this is what we have to connect. Solve the problem. Right. If the density of the material increase, the value of Young's modulus. Now use the basic science here. Okay, the science of the material. This is material science. Okay, and then comment on this. See, now here you understand, density of a material increases. Hello?
Yes, sir.
So now go to the micro level. When the density of a material increases, what happens inside the material?
Lesser free space.
Lesser free space.
Less, more packing and less white spaces.
Okay. Come down still, come on.
Strongly packed.
Strongly packed. See, there is some physics term that you have to
Stronger forces of attraction between.
So therefore, you see these, when you are talking about this, basically what are the forces that are binding the molecules? It is electromagnetic forces. Correct? Hello?
Yes. Yes.
So when you say you are going to see, you have taken some material, its mass is m. That means the number of particles put together, its mass is m, and it is occupying certain volume, right? So there is intermolecular distances between each of the molecules. Now if you make the material denser, that means mass remaining same, volume is decreasing. That means the molecules are coming closer. That means the interatomic forces are much stronger now.
Yes, sir.
The interatomic forces are much stronger now. Okay. Now if you want to strain that material, you have to work against the intermolecular forces. Correct?
Stress increases.
Isn't it? You have to work against the intermolecular forces if you want to cause some deformation. Isn't it? And that is the reason why you see, if the density of a material increases, we are not taking two materials of two different densities. The same material, if the density increases, then as the packing goes on increasing, then the capacity to deform it, or the external forces, the capacity of the external forces to deform it goes on reducing. Okay. In other words, that means the material acquires a property to oppose, it gets more capacity to oppose the external deforming forces. Okay, and therefore, and how do you measure? What is Young's modulus? Young's modulus is a measure of how much stress it is developing. Okay, how much stress it is able to develop. If the material can develop more stress, that means its Young's modulus is more. Got it? So that is the connection between the two, and therefore it will increase. Got it?
Yes, sir.
Yes. The following four wires are made up of same material.
Previous question.
Previous question.
Yes. Sir, can you give an example, sir, where Young's modulus first will increase, then decreases?
Young's modulus first will
increase and then.
No, I don't know. There are some materials which are anomalous, just like water. Okay. So in those cases. Right. The following four wires are made up of same material. Which of these will have largest extension for the same tension applied? So they are told same material, that means Young's modulus is same. Right? And same tension, force is also same. Okay? So these two factors are same. Okay? So therefore, our formula simply becomes F by A will be equal to the original length L divided by A into delta. This is it. So this is a constant. This term is a constant.
So delta L we want.
So this is from the information that they have given, I have coined the mathematical model of whatever data that they have given. Okay, now because you have to compare. So, which of these will have largest extension? So, that means now we have to think about this. So, we have to think about this. So, therefore, here you see, so here, so there is a constant term here, there is a constant term here. So, delta L into some constant K will be equal to L by A. Correct? Hello?
Yes, sir.
So, now here, when the same, which of these will have largest extension when the same tension is applied? So, you have to compare L by A for all of them. That's it. And they have told wire. So, they are given diameter. So, you convert this into L by pi r square. So, if whichever L by r square is more, then in that the delta L will be more. So, they are all given diameters here. So, make your life simple. L by pi d square by 4. So, again this is a constant. So, you can write it as again some other constant k1. So, you can push that pi by 4 also this side. Okay. So, this becomes another constant. Delta L is equal to L by d square. So, which one will have more? See, something simple it is given, 55, things like that. All are centimeters length, this is millimeters. You should not take so much time. Option A, isn't it? Hello?
Yes.
This is option A, that's it. Option A, the right option. Correct. Got it, all of you?
Yes.
So, you see, from the given data, you establish the math model. And when you are going to compare, try to get the math model so that comparison becomes easy. Okay, and then do it. That's it. Okay, so in other words, you see delta L is proportional to L by D square. Right? So whichever has got more, that will have strength. Okay. Load versus elongation graph for 4 wires of same material. So same material means Young's modulus is C. The 4 wires of same material and same length. The original length is also same. Okay. Then I show you the thinness of the wires. That is, you have to get the area. So again here Y by L is constant. So and the force F, okay, divided by A into delta. Right? Again, this is the constant. So the graph that you have got is now what? F by delta L. The load was 4 wires of same length are shown in the thinnest of the two. So now you have to attack this. You have to attack this.
Yes.
So how will you attack this problem?
Sir, we can manipulate that as A is directly proportional to delta, sir.
No, from the graph you have to pick.
That's what, sir. F by delta L is the slope of the graph, sir.
F by delta L is the slope of the graph, correct?
A is directly proportional to the slope of the graph.
A is directly proportional to slope of the graph. Okay, fine. So since this is there, A is directly proportional to the slope of the graph. Good. Right. A is directly proportional to the slope of the graph. Okay, fine. Good way of thinking. So the slope of the graph is thinnest is 0A, OA.
OA, yes.
Okay, OA. So this is correct. Well done. Excellent. So this is how you have to abstract. See now Adil picked it up, like how to use the formula and manipulate it. Or other words, if you don't want to use, at this stage if you want to do it, you draw a line like this, a parallel line like this. Okay, a parallel line like this. Okay, now that means now force is constant. So you have made this force also constant. Okay, hello? Now you will measure the, now you have made force constant. Okay, and now it is a question, since you have made force constant, you can pull that force also this side. Okay, and again you will find that area. That way also it. Okay, fine. Can we proceed, students?
Yes. Yes, sir.
Yes, please. A fixed volume of iron is drawn into a wire of length L. The extension produced in this wire by a constant force F is proportional to. So again, they have taken this wire. Okay, so you write the basic formula. Y is equal to, right? So here y is equal to F into L by CA into delta. Okay. Now they are told fixed volume. So bring the concept of fixed volume. So multiply and divide by L. So this becomes F L square by A into L. If you do, you will get the volume. Okay, and then you will have delta. Clear?
Yes, sir.
So and the force they have told is constant. Okay, and V is also constant. Y is also constant. So again you will get something constant here. Constant is equal to L square by delta. Okay, an extension produced by the wire by constant force F is drawn into thin wire. For a fixed volume of iron is drawn into a wire of length L. The extension produced in this wire by constant force F is proportional to.
Delta you can take on the left hand side, sir. Constant you can bring down.
So
delta equal to constant times L square.
So it will be proportional to L square, isn't it?
Yes.
So 8 then it is proportional to L square. Everybody got this?
Yes, sir. Yes.
That's it. So delta L is proportional to L square. C proportion. Right? So this is all. You have to just see, if you know the basics, you can just calculate and do it. Right. Two wires of same material have lengths ratio 1 into 2. Two materials of same wires of same material. Young's modulus is same. Length is 1:2, and the radii are in the ratio 1:root. So wires means cylindrical. So pi r square. Right. By inspection, you should be able to tell. You should not take so much time now. Come on, sharpen your brains. See, right away you can see there, the numerator is 1. See, L is coming in the numerator for both. If you write y is equal to FL by A delta L. A is R square. R square is coming in the denominator, L is coming in the numerator. In L, first L and another one is 2L. And in the denominator, R square and root 2 will come. So 2 will get cancelled. 1. So the increase in their length will be 1:2.
Yes.
Okay. See, you have to strengthen your conceptual clarity, and you should develop the right attitude. See, if you want to simply learn science, well, aram se learn science, no issues. But if you want to learn science and then also compete in the competitive examination, so along with science, you must also develop the right attitude. So you have to work on that front, and you will develop good attitude provided you work for it. What is that? You enjoy solving the problems. Don't put any stress on yourself. That is the basics. That's the basics. If your mind is calm and cool, then a lot of things you will learn. But if you put your mind under stress, then you will not learn. And don't sit here to prove a point. You are just sitting here to learn science, conceptual clarity and problem solving abilities. That's it. Okay, shall I proceed? Hello?
Yes, sir.
Somebody will tell me it's 8:30. Okay, still 10 minutes. The area of the cross section of the wire is so and so, wire length they have given. So area of the wire, so length they have given. Okay, original length they have given, and then they have given the area. Okay, now this is how I solve the problems, because I will not look into the numericals. It is loaded with 1 kg. So it is loaded with 1 kg. That means the mass is 1 kg and the force is 1 into g. Okay, Young's modulus is given. Okay, then increase in length will be. They are asking simply the increasing length of this. So, what's the difficulty in this problem? All the values are given.
Yes.
Okay. So, how would I solve this problem? 1.1 is equal to the force. Force will be 1 into 10. Okay. And L, the original length, is 1.1 meter. I am not writing all the things. You know my style of working. And the area they have given is 1 millimeter square. You can convert it into meter square. And delta L. What is delta L they have given? Okay. The increase, then the increase in the length. They are asking you the increase in the length. Correct? Hello?
Option is
So that means now you see it's all 1, 1, 1, 1, 1. So whichever option has got 1, yes, there are 2 options, this and this. There are 2 options that are there. So one of these 2 options should be right. Got it? So you have to write the values here, write the values, this one and all. Anyways, here, these things will get cancelled. Okay. But 1.1 into 10 to the power of 11 will remain, and this 10 is there. So therefore, this becomes 10 to the power of 10. Okay. Hello? And this is 1.1 meter, no issues. And this one area they have given is what? The area of the cross 1 millimeter square. So area of the cross section is 1 millimeter square.
10 to the power minus 6.
10 to the power of minus 6. Okay. So if you multiply it by 10 to the power of minus 6, you will be left with 10 to the power of 4. Okay. And this will be what equal to 1 upon delta L. So delta L will be equal to 1 upon 10 to the power of minus 4. That means millimeters, 0.1 millimeters.
Yes, sir.
Correct? 0.1 millimeters. So
Yes.
we are going to even quickly calculate this. Correct? Without any confusion. Right.